Let's talk about some of the upcoming due dates before we go ahead and get started here. So, all right, microphone's on, I'm presenting. All right, good. So discrete random variables was due last night, so hopefully you all did that by now. And so the next homework coming up is the homework on binomial probability distribution, along with the corresponding quiz that is due the 18th and the 19th. That is Thursday and Friday respectively, or in other words, tomorrow and the following day. And we'll definitely get through 7.1 today. I'll make that due Monday. This one, the one on the normal distribution, it's only got 7 questions. It's a very easy homework, very easy. It's just a bunch of terminology. So I'll make that due Monday, but honestly, you can get that done with, and if you click around enough, you'll get that done in 10 minutes. So I'll make that due Monday here momentarily. But those are the 3 assignments coming up. And besides for that, I think that's all I have before we start the lecture. Does anyone have any questions before we begin? Okay, so let's go ahead and get started. So the course notes are updated with some of the new material from chapter 7, which is on normal probability distributions. Now let's kind of think about what we've talked about already. What we've talked about already is discrete probability distributions. So virtually, we look at data that is countable and we analyze it accordingly. We figure out probabilities for one data point to occur, or at least some set of data points, or at most some set of data points. We dealt with those inequalities, we flipped them around, and we figured out some probabilities. The only difference between that section and this section is now we're looking at continuous, these continuous random variables. So the things we're going to be dealing with won't be, what's the probability that the number of siblings is blank? Because the number of siblings would be something whole and countable. Now we're going to deal with things such as well, anything that's continuous, like speed, distance, time, these variables for which we can have minuscule or decimal approximations. So we can have decimal representations of things. And so when I refer to continuous random variables, really what we're going to be looking at. So we could technically look at 2 of these, but I chose to just look at one in particular called a normal distribution. That's going to be the most important continuous random variable that we look at. So we're looking at normal random variables here. And when I say normal, I mean we're looking at any data set whose values are bell-shaped and symmetric. And I put an example here. So if you did some data, maybe this represents IQ scores. Or yeah, so this could represent IQ scores or something, or it could represent heights or other dimensions of a certain animal or something, and some measurement. In any case, we see that the data is roughly bell-shaped and symmetric, as you can hopefully see by this red line that's drawn to represent the data. And so this is the visual representation of data we will be looking at, just anything that is bell-shaped. Now this red curve that I drew, it's what's called a normal curve. So this is going to come up a few times. It's called a normal curve, which is, it's used to describe continuous random variables that are normally distributed. So anytime you hear me say the word normally distributed, just know that I'm referring to a data set. I'm referring to a data set such that its general trend is represented by a bell shape, or this red curve here, this normal curve. So that's what normality is going to mean in this class in terms of distributions. And again, normal curves, normal distributions are very prevalent in many different facets of continuous variables. Pretty much any class, if a teacher computes the grades at the end and produces a histogram of the grades, almost always takes the shape where you have, well, hopefully, typically you have a bunch of C grades, you have less C and D grades, and then you have even less A and F grades as it slowly fizzles out as you get further away from the middle of the data. This is used with heights of individuals, weights as well. There's a whole bunch of different applications, heartbeats of individuals. This is used a lot to get expected values and understandings of people as a whole based off of the trends of perhaps some sample, like we've talked about in the beginning of this semester. So let's go ahead and talk about a normal distribution, just in a slightly more formal sense. A normal distribution is well, it refers to a continuous random variable. So we say a continuous random variable is normally distributed if its relative frequency histogram, just like that illustration right above, has the shape of a normal curve. So exactly like the example immediately above it. So if it looks like the shape has a bell shape and it looks symmetric, that's another idea, it needs to look symmetric as well, then we would say that that's normally distributed. And if a continuous random variable is normally distributed, it's not just a continuous random variable, it would be a normal random variable, which I'll mention later on. So as you'll see with this section, we're going to be dealing with a lot of terminology. And again, the homework for this section, super easy. You can knock it out really quickly after I demonstrate some of the terminology here. So now that we've kind of talked about normal distributions, we also need to reference how to find the probabilities, because that's what we did in the previous section. We found probabilities for discrete random variables. What about for normal random variables? Well, there's a problem though. It actually uses a bit of calculus to think about, but I think I can also convince you all by just showing it empirically. It's more difficult to find the probability for a specific continuous random variable in general, because it's continuous, there are technically an infinite number of outcomes. The book gives a really good example of this, where so the book gives a really good example. Hey ladies, can you go ahead and close your laptops? You should go ahead and pay attention to this lecture. Thank you. So, so there are technically an infinite number of data points. So if you tried to figure out the probability, remember we approximated this probability as a relative frequency in the very beginning for the discrete random variables. And what we normally did was we figured out the frequency of that occurrence. Maybe something occurs one time, and we divided that by the total number of occurrences. But if continuous random variables have an infinite number of values, again, the book says perhaps someone showed up 19.2387 minutes late to class. And the only time that happens is once. But with continuous random variables, technically we are over infinity different options. There's an infinite number of outcomes, because continuous means that we can have really small. So is that Sports Center? Yes. Okay, I thought I recognized that. Okay, so because of that, 1 divided by infinity really comes out to 0, which you don't have to know why that's a calculus thing. But if we so what this is saying though is if you try to figure out the probability of a specific continuous variable, and it says it on this description down here at the bottom, the probability of a particular value ends up being 0 because of this idea. So we compute over an interval of values. So like we did a few chapters back, whenever we had classes and class widths and stuff like that. So notice the histogram above, that's not a bar graph, it's a histogram, which does have a slight difference. Because notice the 100 is not immediately below the box, but instead it's the border of one of the boxes. Same with 90, and this is 95. Notice that the box is happening within these intervals. That's saying that this histogram is not counting the number of times 95 occurs or the number of times 100 occurs. It's counting the number of times something occurs between 95 and 100. So these intervals are ultimately what is what our X values are going to look like. And so we slowly start to introduce something called a probability density function, which is basically a formalization of this curve. So with this curve in mind, we're going to scroll down to this definition. And technically, you already know this definition in a more simplified manner. It generalizes, though, to a continuous random variable. So a probability density function, it's an equation used to compute probabilities of continuous random variables. The only thing I'm really going to focus on are these two properties down here. The total area under the graph must equal 1. Now, when I say graph, you can think about the bell curve right here. The area under this red curve, if you were to shade in that whole region and figure out its area, the area underneath this curve right here, so this whole part, this is all equal to 1, the area of that. Hence a density and not a distribution. It's a density, refers more so to area. And this is symmetric to this idea that when we were dealing with discrete random variables, all the probabilities had to add up to equal 1. It's the same idea, except we're transitioning from discrete, where we do have countable probabilities. We have a probability of 0.17 and a probability of 0.28 and all of those, and we just add them together to give 1. But instead, we have an area, and so that area must equal 1. Additionally, the height of the graph must be greater than or equal to 0 for all values of the random variable. So basically what that says is that your graph better not fall below the x-axis. Your graph should converge towards the x-axis. And we'll see examples of this. Actually, I have a few examples in example 1. We'll see this, but just kind of a precursor, this is not good. This right here is not good. The graph cannot go underneath the x-axis. That's what I'm referring to. But we'll get back to that. So those are just two generic properties of continuous random variables in general. Now we're looking at, well, a specific type of continuous random variable, a normal one. So basically when we have a very nice bell-shaped distribution of data. And so the simple function that we're going to use is given right here. Okay, I'm kidding. We're not using this function, but it's a pretty complicated looking formula. We're going to use a much easier way of dissecting this formula. And if you were curious, exp is that little e command in the calculator. E raised to the negative x minus mu squared, blah, blah, blah. But you don't have to know that. I just figured that's more so food for thought, that this is the formula going on behind the scenes, but we don't have to use it. So instead, really how we're going to find, so instead of using this formula, well, we have to use something else. Well, what we're going to use instead is a graphical representation of this formula. And we're going to figure out, so this formula represents ultimately the area under this curve for certain regions. Now, how we interpret this, we'll figure out how to interpret this gradually. But the first idea is that we understand that we're looking at the curve to figure out the area underneath it. And what does that area correspond to? The probability of intervals of continuous random values. And so this is the normal density curve, or just the normal curve. And it has a few properties that we need to abide by, and also a few properties that will help you answer a few homework questions. So the properties of the normal density curve. Well, the first one is it needs to be symmetric about the mean. So what I'm going to do is, as I state these, I'm going to go back and forth between the next problem so I can demonstrate what that means. Because the next problem has some that are right, some that are wrong. One of these is not symmetric about its mean. Hopefully it's clear which one this is. What's that? Yeah, it's the first one. The mean's right here. That's not really symmetric, is it? Stuff happening on the left isn't the same as on the right. So this one is not a normal curve. It has to be symmetric. So if you want an example of something that isn't symmetric, that's a good one right there. The rest of them are. So let's keep going. So that's the symmetry one. The normal curve has a single peak. I'll pretty much simplify it as simple as that. So I don't have an example written down below. I think there is a homework question that'll ask if something that looks like, so this here, it will have a curve that does this number with 2 peaks. That can't happen. You have to have a single peak. So this would not be allowed. You can only have 1 peak for one mean. The next point, you don't have to worry about the inflection points too much. That's more of a calculus idea, so we'll skip that. The area, so we already stated this, the area under the normal curve is 1, which that is inherited from the probability density function that we talked about up here. So again, the area under the curve is 1, which of course we can't really figure that out with no numbers or anything given to us. So that'll just be assumed. So we're actually going to utilize this quite a bit, but we can't really prove this. We'll just be given this information. The area under the curve to the right of the mean is 1/2, and to the left of the mean is 1/2. Now this actually makes sense. If the area under the curve is 1, and the curve is perfectly symmetric, that means if I split the area in half, just right down the middle, 1/2, 1/2. That's it. And that'll answer a homework question right there. So you're welcome. So that's, I think that's already 2 homework questions right there out of 7. So not too bad. Let's keep going. As x increases, the graph approaches the horizontal axis, but never reaches it. This is true as x decreases. Now, what does that mean? As x increases, the graph approaches, but never reaches the horizontal axis. This is the same as x decreases. Let's look at those examples down below. I'll come back to this momentarily. So this is saying that the tails of the normal distribution, well, they can't reach the horizontal axis. So stuff like this would be bad, which is what I mentioned before. Cannot cross the horizontal axis. Notice this one crosses it, so this one's out. It's saying that the tails have to pretty much level off and virtually look like it's parallel or even overlapped with the horizontal axis, but it never quite does. In fact, it converges. That's a fancy word to use here. So it converges. So if we look at the graph right below it, that does not exhibit that characteristic. The tails cannot just curve right back up. The curves have to level out, in other words. That's the main idea here. So the tails have to level out with the axis. So that means the top right one would be a perfect demonstration of a normal curve. Because notice the ends start to slowly level off, and they start to slowly converge with the horizontal axis. And then with all of this going on, the empirical rule is still in effect. The empirical rule is going to help us out a little bit here. And what the empirical rule says, I went ahead and just summarized it here. 68% of the area is between 1 standard deviation, 95% between 2, 99.7 between 3. So this is still true, because this corresponds to a normal distribution. So that may help us as well, but just knowing that gives us a good comprehensive insight on what all we have to work with. And so these are the properties of the normal density curve. Now, more so, these are axiomatic, which means really these are assumptions that we will be just given once we're told that we have a normal curve. And in general, you won't have to prove these things. But knowing all of these things when we are given a normal curve gives us a lot to work with. And so again, we went through all the properties and discussed which one of these could actually represent a normal curve. So let's go ahead and scroll down a little bit more to another diagram. Again, this section is a ton of terminology. It's just a bunch of terminology to help us prepare for the next section. A normal curve is always based off of two values, the mean and the standard deviation, which we'll see actually in the next example in this section. So a normal curve is based off of the mean and the standard deviation. If you have a different mean, you're going to go left or right. This is because the mean represents the center of the curve. So if the center of the curve gets larger, then guess what happens? The curve itself will shift. Or if the mean gets smaller, well, the curve is going to shift the other direction, because the center of the curve always has to be the mean. Now, if you have a different standard deviation, so when we defined standard deviation, conceptually what we discussed was the standard deviation represents how much the data spreads. If you have a large standard deviation, the data is going to spread a lot. If you have a small standard deviation, it's going to stay really close to the mean. So on that rightmost diagram in the notes, this red one right here, this has a much smaller standard deviation. Everything's very compressed, as opposed to the other one where it has a larger standard deviation. So we can see that the data being spread out is directly proportional to the shape or the width of the normal curve. And then here's some overlays to sort of illustrate this. But let's go ahead and see how we would construct such a normal curve if we're given a template. So it's very minimal work on our ends. So suppose the number of emails Brad gets in a week. Suppose that's normally distributed with the mean, so I get about 34 emails a week, give or take, and a standard deviation of 7. So you can expect me a decent bit of the time, or a majority of the time, to get anywhere from 7 standard deviations below that or standard deviations above that. And that's pretty much my week in terms of emails. Of course, when a major test comes up, I get a lot more. So we're going to draw a normal curve with the parameters labeled. So I gave you a template here, and online they will also give you a template. The middle of the curve always has to be the mean. So we know the mean's 34. The mean always tells us the center of the curve every time. So that's why I'm immediately going to put 34 here. Now the question is, if 34 goes there, what goes here and what goes here?
7 minus 34 for the left and 34 plus 7 for the right.
Yeah, so we're going to go ahead. So remember, these outer ones, this is going to be, well, the generic labeling for it would be whatever the mean is minus 1 standard deviation below. Well, I mean, you answered the question. You answered it correctly. In general, it's the mean minus the standard deviation, which is exactly what you said. We know the mean is 34. In fact, the mean is 34. And we know the standard deviation below, because we're going less than the mean, is 7. So it's 27 on that side. And then very simply, the only difference on the other side, in general, it's mu plus sigma, or the mean plus the standard deviation. So that's 34 plus 7. 41. So that would be the construction of the normal curve with the parameters. So that's how the mean and the standard deviation help us construct the normal curve. It's as simple as that. The shape stays pretty much the same relative to scaling, which here, if we're given the template, we don't have to even worry about that. And you figure out the middle. The standard deviation tells you what increments you would continue in. So if you keep adding 7, say if you added 7 to 41, that would give you the next increment. If I had that labeled here, you would keep subtracting 7, that would give you more increments the other direction. But this is sufficient. So we're going to scroll down a little bit. Shade the region that represents the proportion of emails per week less than 27. Well, we already have the mean and other adjacent values labeled. So I'm just going to carry those down directly. We already figured that out in the top part. And all it's asking for is shade the region that corresponds to less than 27 emails. Well, that sounds easy enough. 27's right here. So let's just shade that region because it's less than 27. So let's shade less than 27. And that's it. That's it for this problem. It will legitimately be a multiple choice question in your homework that says, shade the region that corresponds to, say, less than 27, or whatever example it provides, whatever word problem it does. It's that simple. Now, this class, you don't have to worry about an equal sign or not. You don't have to worry about that this is x is less than 27. That doesn't matter. Because as we said, we don't care if a value is equal to a specific number. We care about intervals. So whether it says less than or at most 27, we treat it the same way. So simple as that. We shade, and notice we're shading with respect to the 27. Okay, let's do that again for greater than 48. So there's 27, 34, 41. Well, the problem is there's not a 48. Yeah, you go a little bit past 41. Yeah, just like that. So that actually ends up being 2 standard deviations above the mean. But there'll be a multiple choice part where they'll throw in a 48 for you. So I'll draw a little dotted line here. And then we want to shade, because remember, we're shading greater than 48. So, okay, simple enough. We just shade what's greater than 48. I'm going to be mad if there's one of you that does not get 100 on this homework. This is literally 2 of the problems right here that I just kind of shoved into one. There's also an interpretive part, which again is pretty straightforward. So this is in relation to part C. Suppose the area under the normal curve to the right of 48, just like what we did, is 0.0228. How do we get that number? Don't have to worry about it. They're just giving you the area under the curve. Therefore, the probability is, well, there's the 0.0228, that the number of emails Brad receives is more than or less than 48. Well, is it going to be more than or less than 48? Use the graph to help you.
Less than.
Notice here's 48, and we shaded the region greater than it, or more than. It's going to be more than. It just basically wants you to, I guess, find the wording that corresponds to greater than 48. So greater than 48, what's synonymous with that? More than 48, that's it. And you can use the graph to visualize that as well. Because we're shading more than 48, 49, or 50, or 51. And that's really this section. That is as much variety as this section gets. It's all a terminology-based section, so we can kind of prep for the upcoming section. So again, this homework is going to be due Monday. You can knock out this homework very quickly. You can knock this one out very quickly. 7 questions. Most of them look like this. It's very boring, but you can get it done with probably in 10 minutes. Does anyone have any questions for me before we look at the next section? If not, let's go ahead and do exactly that. Now, really the last section was a huge stepping stone for us to transition into this section on normal distribution applications. Now that we have a little bit of an idea of what kind of objects we are dealing with, now we need to figure out how are they relevant? Why do we care about them? And so one incredibly helpful thing that we can do. Well, let me back up. So to find the area under the curve, we haven't really done that specifically yet. We know that the area under the curve on each side of the mean is 1/2. But what about if we wanted just a certain segment of the graph, or we wanted to figure out the area under the curve that's to the left of a standard deviation? How would you figure out specific stuff like that? And that's when we're going to use, well, we're going to start off using a table that I've now added to the notes, to the appendix, table 5 as it's called in the book. And also the aid of technology as well. And so we'll look at this table and how to interpret it momentarily. It seems like an intimidating table, but it's really easy to read. We just need to make sure we know how to interpret what we put into that table. But this first idea that we're going to talk about is standardization. And this is incredibly, incredibly helpful in analyzing statistics. So what you're doing, so we are assuming that we have a random, we have a normal random variable, x. We make that assumption, which means we get all of those really nice properties. So in other words, we have a data set that is normally distributed. And so we could think about it as grades in this class. The grades in this class are, in fact, normally distributed. We have a good bit of C's, some D, less D's, less B's, and then less so A's and F's. And this is pretty common for every class. So with a class grade or a set of class grades, we're going to have a mean and a standard deviation that we could figure out if we wanted to. But then there's this transformation that we can do called standardizing. And what this does is it takes that information. So it takes, say, the class grades and it normalizes them. It shifts everything around. It takes our curve, and I'm going to scroll up right fast. It takes our information and centers it to 0, and it makes a standard deviation of 1 exactly. And this is very important because once we standardize a collection of data, and that means we can use either that table in the back of the book or technology to figure out the area under the curve for a particular region. And this is incredibly helpful. But we're going to start off with examples where we already have this standardized for us. So basically, there's two things now we're kind of juggling here. There's just a normal random distribution, which is just, a collection of class grades, the heights of people, the weights of people, the heartbeats of people. That would be normal. It's got its own mean and standard deviation. That's whatever it needs to be. And then there's standard normal, a standard normal. So not a normal, but a standard normal. And standard normal means you definitely have a mean of 0, and you definitely have a standard deviation of 1. And all that's a fancy way of saying is once you have a mean of 0 and a standard deviation of 1 in a normal distribution, you get to use all of these resources for free. So that's why this is so helpful, that we can do this. You get a lot of properties for free. And I keep alluding to it. You get to use this table for free because this table is on the assumption that you have a mean of 0 and a standard deviation of 1. And again, it looks more intimidating than it is. It's really going to be just a lot of comparing. There's no computation here, though, so that's good. Okay, so let's figure out how to use that table, because that table, when I first saw it, I thought it was very intimidating. So let's just talk through how to use it. So in example 1, we are already under the assumption that we have a standardized normal curve. So basically, they're already saying you can use the table for free. So we're going to use the table for free. Now, it says the area to the left of z is equal to 1.47. Does anyone happen to remember what z represents in this class?
Z-score.
Z-score. Well, it makes sense. It's called a z. So that's the z-score. So let's just keep that in mind. Z is 1.47.
0.07.
It was kind of hard to hear you with the mask, but I think that sounded pretty appropriate.
It's like you matching.
Yeah, you're kind of just matching. So yeah, so the left.
That's what I kind of figured. I was like, maybe it's not that easy.
Yeah, so Z is 1.47. So let's keep that in mind. Z is 1.47. We're going to scroll down to that table. So notice it has a Z right here. It's got values here, and it's got values here. So we're trying to find the exact part where this says Z is 1.47. So these are all negatives, so they're not going to help us. We don't have a negative in our problem. So wait, they all have negatives. What do we do? Oh, wait, this list continues. So there's a second page for positive Z values, and notice all of these are positive. So I'm going to write this at the top. The Z we were dealing with was 1.47. So the first thing we need to do is find the ones place. So the ones place is going to be in the first column. We hear some ones right here. But it says, 1.0, 1.1, 1.2. We need 1.4, obviously, if anything. We'll worry about the 7 later. So that definitely isolates what we need to find to right here. So we found the row. So that means we're going to be dealing with one of these values straight across, one of those. Which one? Well, that's what the next decimal place is going to tell us. The next decimal is a 7. And so notice up here, it tells us what happens in the hundredths place. We're going to ignore all of these because we want 7. So now we have 1.47. So this tells us the column that we're looking at. Well, we know the row, we know the column. So here's the row, there's the column. Where do these two overlap at? Right here. Well, guess what? That tells us the area to the left of that Z-score. It's just 0.9292. And that's the answer. That's it. So 0.9292 is the answer right here. It's where the row and the column overlap or intersect. So we can scroll up and put, so the area is 0.9292. And that's it. And of course, on the test, I would give you that table, no doubt. Okay, if that was a little tricky, let's do another one. So same exact premise. It's just to the left of Z is equal to negative 0.71. Kaylin, did you figure this one out already? What did you find for it?
0.2389.
0.2389. Let's go and check that. Let's just go and check that just to show everybody how you came to this conclusion. Okay, so we're keeping Z is equal to negative 0.71 in mind. So let's scroll down. I already forgot the number. What was it?
Negative 0.71.
Negative 0.71. Okay, thank you. So we have a negative for our Z-score. So the first table is going to be perfectly sufficient. It's got the negative sign. It says we start off with a 0.7. So let's go find a 0.7. Well, found it right. In fact, I'll use red here. Right there. There's negative 0.7. So I'll go ahead and highlight that. I don't care about the rows above and below. So if anything, that's the row. We just have to find the corresponding column. Well, the next one is a 1 in the hundredths place. That corresponds to this column. That's a 1 in the hundredths place. And lo and behold, look at what the answer is. Exactly what you said, 0.2389. So that's how you use this table. When you're given the z-score, you have to just break down the z-score by the ones place, the tenths place, and then separately the hundredths place. Is that pretty straightforward so far? 0.2389 though, and that's it. 0.2389. So this is, in fact, valid. And we can remove the cumbersome question mark. All right, so let's make this a little bit more complicated. Now, all of this has been done with the assumption that we've been looking at the left of the z-score. And the reason why this is important as opposed to the right is because our graph here always looks and always analyzes to the left of the z-score. Notice this is all happening to the left, not to the right. You might think, well, what about the next graph? No, that one's also to the left. So this table can only be used when we are looking at the left of the z-score. So you might think, all right, well, what happens if we try to look at the right? Well, you might see something fairly familiar here. So let's scroll up and look at part C here. The area to the right of z is equal to 1.55. Well, again, our table doesn't help with to the right, but we can look at, so if it's to the right, then we really have to break this down into two parts. With the first part being very familiar. Let's find the left of that value. Same exact value. So we're looking at the complement. So if you remember what the word complement might imply, then you might already know the answer here. But if not, we're going to say, let's find the left version first so we can actually use the table, and then we'll figure out how to account for that. So we're going to do the same exact thing we did before. We're going to find the area that corresponds to the left first, and then figure out how to accommodate that or transition that to represent the right. So 1.55, this is a positive z value, so I'm going to skip all the negative z values, and I'm going to go to the next table. What was it, 1.55? Z is equal to 1.55. So the first thing we have to do, find 1.5. Okay, well, 1.55 or 1.5 is right here. Simple enough. Okay, and next digit is a 5 in the hundredths place, which tells us we look at this column. And we get 0.9394. Okay, cool. That's our area. Simple enough for the left, 0.9394. So that is to the left of the curve.
You subtract that from 1.
Yes, that's it. You subtract that from 1. That's the complement. So exactly. So the right of this value, basically what you found is, all right, see, this is how we're utilizing that the area is 1 that we stated in the last section. This is how we're utilizing that. We know that the total area has to equal 1, and we know one of the sides, which means we have to figure out the other side. Someone figured this out already?
Yeah, it's 0.0606.
0606. Okay, cool. And so that would be the answer for part C. So hopefully that's all pretty straightforward stuff. Very important stuff that really, doesn't take too much to really always mix up the definitions of extrapolate and interpolate. I think this is It's extrapolation. Doesn't matter. It's one of those two. Okay, let's do another one just in case someone might have gotten lost there. Same problem, just different z-score. The right of z is negative 0.07. The fact that there's a negative there doesn't really change too much. It just means we're going to look at the first table because that one has all the negative values. So, is it negative 0.07?
Mhm.
Okay, cool. So we start off with the first two digits, negative 0.0, which that one's all the way at the bottom. All the way at the bottom here. Negative 0.0, and then 7 is the next one. We should highlight that in red. This one in blue, which tells us we are looking at this column right here. And we have 0.4721. 0.4721. And this should make sense that we have an area close to 0.5 because an area of 0.5 is, well, that's 1/2 of the normal curve and 1/2 on the other side. We have a z-score that's almost 0, which means that this z-score is very close to the mean, which is the middle divider. So it makes sense that we have an area that's fairly close to that. And then from here, I think you all see where to go from here. Just subtract.
It's 0.5279.
You said 0.5279. Cool. Area is. Okay, and that's it. So hopefully that's pretty straightforward stuff on how to interpret the table. Does anyone have any questions from here? All right, let's combine these ideas together. So you might remember this. You might have done a problem like this, maybe not with this wording, but this might have come up in Math 105 when you're trying to figure out the area. If you were using the empirical rule to figure out the area to the left plus the area to the right of something. But let's kind of look at it from a more refined approach. So now they want us to find two areas separately and then add them together. So basically it's just combining to the left, to the right, and then you add them together. So this is going to take a little bit of time. To the left of z is equal to -3. So we'll find that one first. I'll kind of label this. I'll just break down my steps here. Really, it's just going to be using that table a lot. Left of z is equal to -3. So let's go find that one. So it's just -3, which is technically -3.00. So it seems like it's, here's -3. And here's 0 in the hundreds place. 0.0013. Okay, that's the first one. 0.0013. I guess I want to write the area is 0.0013. And this makes sense that there's not much area to the left of this because this is a very far out z-score. Z-score of -3, that's normally pushing it. And we don't have to complement it because it's to the left. So let's just move on real fast. Well, if we figure out to the right, that means we need to figure out to the left and then complement it. So pretty boring stuff. So to the right of z is equal to positive 3. Let's go figure out the left area of 3. So 3 corresponds to 3.00, and we can find that value. Hopefully it's clear to everyone that we can find that value right here. It's 3.0, it's right here. And then the first column is 0 in the hundreds place. So it would be 0.9987. Okay. But it says to the right, which means we have to subtract it from 1. Is that 0013?
Yeah.
Okay, cool. So that's step 2. Notice because it said to the right, I had to complement it. And then step 3, well, guess what? We just add them together. And it makes sense that they are, in fact, the same number because a z-score of -3, a z-score of +3, they're the same distance from the mean. And since the normal curve is symmetric, in fact, we didn't even have to find the second one. We could have used the symmetry to answer that. 3, and that is simply 0.0026. Okay, let's just do one more, and then move on from there. So we'll do one more, just in case you missed it. Left of z is equal to -0.25. It's the same problem, just different z-scores. Z is equal to -0.25. This one, we just find the area directly. -0.25, we go to the negative version of the table. .25. The ones in the tens place, -0.2. 0.2, that puts us right here. And then the 5 in the hundreds place, of course, puts us here. 0.4013. Okay, that's the first one. 0.4013. 0. Did someone already figure it out for the next one?
Yeah, it's 0.1357.
I guess for completion, did you figure out what it was before?
Yeah, it was right here. 0.8643.
8613 or 43?
43.
43, gotcha. And then what was the final answer one more time?
0.1357.
So I trust you can all find that by this point. Just to save a little bit of time. And then, of course, we just add the 2 at the end because they want both of these regions added together. 0.013 plus 0.1357. I'm guessing that's 0.5370. Cool. So pretty simple stuff so far. So that's the first fifth of the homework here. So let's look at some other problems. Unless anyone has any questions before I move on. All right, let's move on to example 2, which now says find the z-score. Not find the area, but find the z-score that corresponds to the given region. So we're not given a z-score. We're going to be reading the table in reverse. So they're giving us the area and we have to find the z-score. So they're telling us area to the left, which I guess it's good that it's to the left because we don't have to complement. So we need to figure out the z-score that corresponds to this and figure out how to represent it on one of these templates. Now, we always know that the mean is right smack in the middle. Now, my question is, if we wanted to graph an equivalent standard normal curve to represent to the left being 0.52, where would I draw the line corresponding to that? To the left of the mean or to the right of the mean? So why do you say to the left?
Because it's asking for the area to the left.
Well, to the left of some line that we're going to draw. So we're going to draw some line, and then the area from that line all the way to the very left, or your left, will be 0.52.
So wouldn't it just be the line you already have drawn, this one?
So the line I already have drawn, that's an area of 0.5. But we have 0.52.
So
A little bit to the right, that's correct. A little bit to the right. In fact, it shouldn't be that high up. There we go. So that would represent, so the mean is 0.5. So this would be 0.5, everything I'm shading in red, because that's one of the properties of this normal curve.
I thought the mean would be 0.
Well, the z-score of the mean is 0. The area to the left of the mean is 0.5. So this area, so this is you agree that this shaded region is to the left of the mean, right? So I'm not even I'm not going full yet. That area is 0.5 because that's half of the curve. But we have 0.52, which means we need a little bit more area. So that's why we're going out a little bit further to this line that I drew. So the z-score of the mean is 0. That is true. And in fact, actually, because it is standard normal, you were right on that sense. The mean is always 0 in a standard normal curve. I guess I'll use blue to represent, this is going to be the unknown z-score. This will be the z-score that corresponds to an area of 0.52. So we're basically working backwards. We're not given the z-score to find the area, we're given the area to find the z-score. Really, the homework doesn't ask for this, but I did want to give some visual representation of what's going on. And so let's take this area of 0.52 and figure out how do we work backwards. So an area of 0.52, that's what we're going to keep in mind. So I'm going to look at not the z-scores, but I'm going to look at all of these area values. Ultimately, we have to look at the positive ones because I'm looking for 0.52. And as you go down each row, they get larger. But they only go up to, might be hard to see here, they only go up to 0.5. We need 0.52, which means these values aren't large enough. Which means we need to go to the next graph because notice now these areas get a little bit larger. So we need to find, so this is where it gets a little tricky because we're looking for 0.52 and the homework's going to ask you to round to 2 decimal places. So technically 0.52, if we round to 2 decimal places, could really be any one of these 3. 0.516 does round up to 5.2 when you round to 2 decimal places. 0.519 does as well. And 0.5239 rounds to 0.52. Now, the annoying thing in the homework that I just fixed, they expected you to choose the right one with no margin of error whatsoever. And I found that really annoying because I kept getting them wrong. And I'm good at this stuff. So I changed it to where it wouldn't let me change it any more than it gives you a 0.01 margin of error. So that means it will probably consider the right answer to be this middle one. But if you chose this one or this one, it will also include that to be correct. It'll give you a 0.01 margin of error. So if you find yourself having issues with, and it's one problem in this homework, if you find issues with the one you're on, just try doing a different one. It'll probably work for that one. I'm going to be safe and choose the middle one. But again, this one on the left or this one on the right would be perfectly sufficient. I hope that this margin of error I gave it should be enough for you to get the problem right. So I'm going to choose this one as the closest one, the closest value to 0.52, because it's very, very close to 0.52. That's the closest one. But again, if you chose the one to the left or to the right, that's fine. So again, we're finding the area. That's why I'm choosing this first. And guess what we do to find the z-score? There's the first 2 digits. And then there's the hundredths digit. That's it. We found the z-score. So did I lose anybody there, or is that straightforward? So the z-score we found was 0.05. And this makes sense because a positive z-score means we are above the mean very slightly. And so that does resemble, in fact, what we have. So that's the z-score. That is the answer here. But it would also take, z is equal to 0.04, 0.05, or 0.06. Because technically, all of those do have an area of 0.52 when you round to 2 decimal places. It's just my math lab being picky and me trying to set a margin of error, because I think that's pretty unfair for the most part. So let's do another one. The area to the left, so again, it's to the left. They won't really give you any to the right from what I saw, is 0.39. So here's the mean of 0. And again, we know the mean is 0 because it's standard normal, which means we get that for free. If we were to draw a blue line that represents the z-score corresponding to an area of 0.39, where would we draw that line?
This one would be to the left.
This one would be to the left. And let's see, if it's 0.39, it'll probably be a little bit further. And so this is again to the left. So it's saying that this area is going to be the area that corresponds to 0.39. And we need to figure out the z-score that corresponds to this. And again, it's to the left of the mean because the mean itself is 0.5, but we need an area less than 0.5, 0.39 to be exact. So we need to go to the left of the mean to get smaller than 0.5. Before we went slightly above the mean to get more than 0.5. So the area is 0.39. Let's go back to the table. All right, here's the one with all the negative z-scores. See, I already forgot the area. What was it? 0.039? Say that one more time.
39.
0.39, thank you. Okay, so let's find 0.39 on here. Let's see, I'm going down the rows trying to find, all right, we're getting a little bit closer in this ballpark. There's the 0.3s. So relative to 2 decimal places, I'm seeing, so for 3.9, these 3 right here. All of those technically round to 0.39 after 2 decimal places. So I'm going to pick the middle one because that one seems like the closest one. But again, I think that's how my math lab does it. But if you pick the one on either side, that should also work. So I'm going to pick the one in the middle here. And we just simply figure out what z-score does that correspond to. Negative 0.2, and what's the hundredths place? 8. So negative 0.28. And that's it. So that's how we read it in reverse. So it'll take negative 0.28, negative 0.27, or negative 0.29. Because I did give it a hundredths of a margin of error. So really either one of those answers will be fine because technically they all do correspond to an area of 0.39. Does anyone have any questions? We look at the next one. If not, let's look at example 3 here. Find the z-scores, so we're looking for z-scores again, that separate the middle 16% of the distribution. Okay, well, I want to draw out a normal curve to illustrate this. The middle 16% is going to be, well, let's just draw out something that visualizes this. Say, here's the middle 16%. Right here. So let's say that this area is the middle 16%. So really what this is saying is that the area is 0.16. Because remember, this is a normal distribution. And so the middle 16% will correspond to an area of 0.16. So we need to somehow use the table to understand, well, we're trying to find these z-scores. So Z0, Z1, whatever these are. And so what we need to do, so the table doesn't tell us how to find values in between. It tells us how to find to the left or right. So guess what we can do instead? Instead of looking for the middle value, we can find the outer values. We can find the complement because the outer values, well, if the inner value is 0.16, then the area of the outer areas would just be 1 minus. So 0.16 is in between that. If we subtract that from 1, that'll be outside. And if we divide that by 2, then we get a single region. Because we have 2 regions that are symmetric, and we divide by 2. There's still more to this problem, but I have ran out of time. So we'll finish this problem next time. So don't forget the binomial probability distribution homework is due Thursday. That's the next assignment. Corresponding quiz is due Friday. If you have any questions about the binomial homework, please send me an email. Send it to me earlier rather than very late. Jordan.